Hi Math 7A. Today we are going to learn about scientific notation. Have a wistful Wednesday, and you can tell it's late because I wrote Thursday after that, so I'm going to scribble that out, or actually cross that out. Okay. So today's for your homework, you're going to do IXL Math 8G1, and that's not going to be due until Monday. Go ahead and take out your notebook, and I recommend if you could go ahead and get Metmoji from the TUSD App Store. I've seen some students use this, and it works really, really well. You can import this set of notes. That's why I've made an extra copy as a PDF form. You can import that, and then you can write on it just like I'm writing on it in this video. All right, here we go. All right, scientific notation. Remember, I'm going to go fast. You can pause it whenever you need to. I just want to go quickly so that you can just pause it anytime you need more time. Okay, enough talking. All right, essential question. What's the purpose of scientific notation? So scientific notation makes working with really large and really small numbers easier. So let's take a look at a pattern here. If we have 10 to the first, that's equal to 10. 10 to the second is equal to 10 times 10, or 100. 10 to the third is equal to, go ahead and keep going on your own, 10 times 10 times 10, which equals 1,000. 10 to the fourth, 10 times 10 times 10 times 10, which equals 10,000. Notice I'm putting a 0 on for the number of tens I have. I have 1, 2, 3 tens, a 1 and 3 zeros. 4 tens, a 1 and 4 zeros. 10 to the fifth, using 10 as a factor 5 times, you get 100,000. What do you notice about the size of the numbers as the positive exponent increases? So if you're going from 10 to 100, and then 100 to 1,000, and 100 to 10,000, and 10,000 to 100,000, what's happening each time? That's right, you are multiplying by 10 each time, times 10, times 10. And we see that here. One more 10 each time. Okay. All right, let's talk about large numbers using scientific notation. So we're going to move the decimal to the left, counting the places until we get a number between 1 and 10. And then we're going to take that number and write it times 10 to the number of places we moved the decimal. Okay, that's going to make no sense at all until you actually look at it. Here we go. So if we have 520,000, it's a whole number. Its decimal would be located here. We want the decimal to end up moved so many places that we end up with a number between 1 and 10. So we can move it over 1, 2, 3, 4, 5 spots and have it land between the 5 and the 2. So this is equal to 5.2 times 10 to the, we moved over 1, 2, 3, 4, 5 places times 10 to the fifth. So what it's basically saying is it's 5.2 times 100,000, because that's what that's what 10 to the fifth is, 100,000. So this is a simpler way of writing large numbers so that scientists can use them more easily. So if we have this number, 875 million, our decimal would be here. Since it's a whole number, we're going to move over 1, 2, 3, 4, 5, 6, 7, 8 times, because we want to land between the 8 and the 7 to make 8.75. That's a number between 1 and 10. And then it's going to be times 10 to the, we've got 1, 2, 3, 4, 5, 6, 7, 8 numbers, so 10 to the 8th. Next one. Where's that decimal going to land? We know it starts here, but where is it going to land? That's right here. So we're going to have 7 times 10 to the some kind of positive number. We're going over 1, 2, 3, 4, 5, 6 places, so 10 to the 6th. So this is how we write large numbers in scientific notation. We take our decimal, we move it to the left until we get a number that's between 1 and 10. And then we write 10 to a positive power. That positive power matches the number of spaces we move to the left. Okay, let's look at going the other way. Let's look at getting smaller. So let's throw in 10 to the 0 here. So if we have 10 to the 0, that's equal to 1. If you have 10 to the negative 1, that's the same as 1 over 10 to the first, or 1 over 10, which is 0.1, or 1/10. 10 to the negative 2 is the same as 1 over 10 to the second. Remember what we learned about negative exponents? That it's equivalent to an exponent in fraction form, which is the same as 1 over 10 times 10, or 1 over 100, which is 0.01, or 1/100th. So 10 to the negative 3 is 1 over 10 to the third power, which is equal to 1 over 10 times 10 times 10, which is 1 over 1,000, which is 1,000th. So again, each time we have one more zero between the 1 and the decimal place. Same thing here. 10 to the negative 4 is 1 over 10 to the fourth power, which is equal to 1 over 10 times 10 times 10 times 10, which is equal to 1 over 10,000. So to write 1/10,000th, we'd need 1, 2, 3 zeros after the decimal, and then a 1. In the last one, we have 1 over 10 to the fifth, which is the same as 1 over 10 times 10 times 10 times 10 times 10, which is equal to 1 over 100,000. So we get 100,000th. So we get 4 zeros after the decimal and then a 1. So what do you notice about the size of the number as the pattern continues? If you're going from 1 to 1/10, and then 1/10 to 100th, and 100th to 1,000th, and so on, what's happening each time? Okay, yeah, each time you're dividing by 10. And so on down the line. All right, let's talk about making small numbers. So these were small numbers here. Let's talk about making small numbers with scientific notation. With small numbers, we're going to move the decimal to the right, counting the moves until we get a number between 1 and 10. And then we're going to take that number and write it as 10 to the negative power, however many places we move that decimal. So again, doesn't make a lot of sense until we do it. Here's a really small number. Here's our decimal. Think about, where does that decimal need to go to make this a number between 1 and 10? So that decimal is going to need to land right there between 8 and 9. So you have 8.9, which is a number between 1 and 10, times 10 to the, it's a small number, so it's going to be a negative exponent. And we went over 1, 2, 3, 4. So 10 to the negative 4. So that's basically saying 8.9 times 1/10,000th. Next one. We want to make this number into a number between 1 and 10. So that decimal that's here, right here, is going to need to move all the way to the end here. So we end up with 7 times 10 to the, it was a small number, use a negative exponent, and we moved 1, 2, 3, 4, 5, 6 places. So 10 to the negative 6. Next one. The decimal is going to need to land between the 6 and the 5 to give us 6.52. That's a number between 1 and 10. This was a small number to start with, so it's going to be times 10 to the negative. Let's see how many places we moved. 1, 2, 3, 4, 5. 10 to the negative 5. So we use negative exponents to write small numbers with scientific notation. We use positive exponents to write large numbers with scientific notation. Okay, how about changing it back? If we want to change it back into expanded form, we want to look at the exponent on 10. If it's a positive number, we know it's going to be big, so we're going to move that number of places to the right. If the exponent is negative, the number is small, and so we're going to move that number of places to the left. Let me show you what I mean. So take a look at this first one. What kind of exponent is that? Positive or negative? Okay, so positive exponent, that means it's going to be a big number. So we're going to put our 1.5 down, and we're going to move that decimal place. Think about it. Which way we're going to move it to start making a big number? How are we going to turn it into a big number? Yep, we're going to move it to the right. So if it's here to start, we're going to move it over one. Oops, I want to do that. 1, 2, 3, 4, 5, 6, 7 places. It's going in at the end. All those spaces need to be filled in with a 0. So we end up with, I'm going to rewrite this. We have 1, 2, 3, 4, 5, 6 zeros. So we get 15 million. Next one, big or small decimal, big or small exponent, sorry. We have a negative exponent. Negative exponent is telling us that we have a small number. So I'm going to make some space here. I'm going to write my 3.25 because I don't want to move this decimal to the right. That would just make it bigger. I want to move it to the left. And I want to move it to the left 5 spaces. Oops. So 1, why is that not doing it? 1, 2, 3, 4, 5. And fill in those extra spaces with zeros. We can put a 0 after the decimal too. So just to make that a little clearer, so 0.1, 2, 3, 4 zeros after the decimal place, then a 3 and a 2 and a 5. So again, negative exponent, small number. Last one has a positive exponent on it. That's going to make a big number. So we have that 4.08. We're going to think about how am I going to move this decimal to make it into a big number. That's right, we're going to move it to the right. So we're going to go 1, 2, 3, 4, 5, 6 places to the right. Fill in those extra spots with zeros. So we have 4, 0, 8, and then 1, 2, 3, 4 zeros. So we get 4,080,000. Okay, at this point, I would suggest you go back onto Google Classroom and watch that Powers of 10 video. It does a really good job of showing you why scientific notation was developed, what kind of numbers scientists use, and why scientific notation is helpful. So if you'll notice on the right-hand side when you're watching it, they are showing you the scientific notation, and on the left-hand side, they're showing you the actual number most of the time. But go ahead and check that out. And then just for your own notes today,